There's a place on the ocean floor west of Vancouver Island where the Earth is quietly coming apart. Not in the way it does during an earthquake. Not in a single violent moment, but progressively, one fracture at a time, in a process that researchers had never directly watched until 10 months ago. And on Sunday night at 11:41 Pacific time, a magnitude 5.6 earthquake ruptured inside that exact stretch of torn and fragmenting seafloor. Nobody was hurt, no buildings fell. Earthquakes Canada confirmed there was no tsunami risk and no advisory issued. By every standard measure, this should have been a minor item buried in a regional news brief by morning. It was not. And the reason has nothing to do with the earthquake's size. It has everything to do with the specific location, the specific mechanism, and one piece of geological research that fundamentally changed what we know about the most dangerous fault system in North America. By the end of this, you will understand precisely what that earthquake was, what it was not, and what the one signal in the coming days would mean, if it appears. The United States Geological Survey placed the epicenter approximately 208 kilometers, about 129 miles, southwest of Port McNeill, on the northern tip of British Columbia. Earthquakes Canada, measuring from a different reference point, put it 219 kilometers southwest of Port Hardy. The depth came in at a preliminary 10 kilometers, roughly 6 miles below the seafloor. A reviewed moment tensor solution later suggested a source slightly deeper, somewhere between 11 and 12 kilometers, which is approximately 37,000 feet beneath the surface of the ocean. The event struck in open water, more than 200 kilometers from the nearest inhabited coastline. That is why nobody was injured. That is why there was no disaster. But the shaking told you something significant about the rock this rupture occurred in. Felt reports came in from across northern Vancouver Island, from Campbell River, roughly 300 kilometers away, from Port Alberni, roughly 330 kilometers away, and from Metro Vancouver, more than 450 kilometers to the southeast. There were felt reports from parts of western Washington, including the Seattle area. That is a very large felt footprint for a 5.6 at shallow depth. Cold, dense oceanic crust carries seismic energy that would have been absorbed and dampened in warmer, more fractured continental rock, traveled hundreds of kilometers through this material, and still arrived strong enough for people to feel. The earthquake announced itself across a remarkable distance precisely because of where it lived and what kind of plate it happened inside. Within hours of any significant earthquake, seismologists produce what is known as a moment tensor. Solution: a mathematical description of the geometry of the fault that ruptured and the direction the two sides moved. The diagram that comes from it is called a beach ball because of the way the black and white quadrants are arranged on a sphere. And what this beach ball showed was striking. Two possible fault planes, both nearly vertical, one dipping at approximately 77 degrees and the other at approximately 86 degrees, which is just 4 degrees from completely straight up and down. The motion was overwhelmingly strike-slip, meaning the two blocks of oceanic crust slid sideways past each other rather than one pushing up and over the other. That single geometric detail answered the most. Question immediately. A Cascadia megathrust earthquake works by a completely different geometry. In a megathrust event, the oceanic plate is forced beneath the continent along a broad, gently angled contact zone that dips shallowly across hundreds of kilometers. It is that gradual, enormous interface that locks under pressure, accumulates centuries of strain, and then releases catastrophically, lifting and dropping entire sections of seafloor and generating the vertical water displacement that becomes a tsunami. A fault dipping at 86 degrees and sliding sideways does not do that. Earthquakes Canada could rule out tsunami risk with confidence, not as a precaution or a default, but because they read it directly off the mechanism. A near vertical sideways rupture is not going to displace the Pacific Ocean. So the terrifying question, the one circulating almost immediately after this earthquake was reported, got its answer within the first few hours. Is the Cascadia megathrust beginning to fail? The answer, based on the geometry alone, was no. But that answer, reassuring. Know what has been happening in this specific corner of the ocean floor for the last 4 million years, and what a research team aboard a vessel dragging 9 miles of listening equipment through the Pacific finally photographed in detail less than a year ago. The northern end of the Cascadia subduction zone is unlike anything else on the planet's active margins. Most descriptions of Cascadia keep the picture simple. One oceanic plate sliding beneath one continental plate along a boundary roughly of 100 kilometers long, converging at approximately 40 millimeters per year. That description holds reasonably well for the middle and southern sections of the margin. At the northern end, it collapses entirely. The incoming plate near Vancouver Island is not a single clean sheet of oceanic crust moving in a uniform direction at a uniform speed. It is three pieces, each behaving differently, each exerting different forces on everything around it. The Juan de Fuca plate occupies the central portion. The Gorda plate sits at the southern end near California, and at the northern end, there's a small fragment called the Explorer plate. The Explorer plate is the one that matters for Sunday night's earthquake, and the Explorer plate is in serious mechanical trouble. It is being squeezed and sheared from multiple directions simultaneously by the Pacific, Juan de Fuca, and North American plates surrounding it. It subducts far more slowly than its larger neighbor to the south, where the Juan de Fuca plate moves toward the continent at roughly 40 millimeters per year. The Explorer plate manages perhaps 20 millimeters per year in some sections, and published assessments suggest that parts of it may no longer be effectively subducting at all. The mechanical consequence of that difference is the structural heart of this entire story. When adjacent sections of a plate move at different speeds and in different directions, that plate cannot behave as a solid block. It has to deform internally. It bends, rotates, and shears. And a rock plate forced to deform internally does that by fracturing over and over along steep internal faults, and precisely the kind of near-vertical sideways sliding motion that Sunday's earthquake displayed. The Explorer plate is not slowly gliding toward its final resting place beneath North America. It is breaking apart while it gets there. That is the neighborhood this magnitude 5.6 called home, and that neighborhood just got mapped in unprecedented detail. In September of 2025, a research team led by Brandon Shuck at Louisiana State University published a study in the journal Science Advances under the title Slab Tearing and Segmented Subduction Termination, driven by transform tectonics. The data came from a 2021 expedition aboard the research vessel Marcus G. Langseth, which towed a hydrophone array stretching 15 kilometers behind it through these waters, 9 miles of listening equipment dragging through the Pacific, sending sound pulses down into the seabed and recording the echoes that returned from structures buried kilometers beneath the ocean floor. It is the same principle as a medical ultrasound, scaled up by orders of magnitude to image the internal architecture of a subducting slab. What those images revealed had not been seen before in a living subduction zone. 2 active tears were found slicing through the descending slab beneath the northern Cascadia margin, faults cutting vertically through the plate itself and the portion already dragged beneath the continent. Along one of these structures, the researchers measured a vertical offset of approximately 5 kilometers, roughly 3 miles, where one section of slab had dropped relative to the section immediately beside it. That structure runs approximately 75 kilometers in length. That 5-kilometer figure has been significantly misread in coverage of this story, so precision matters here. That offset did not happen in a single earthquake. It is cumulative displacement accumulated over an enormous span of geological time, as the plate progressively bent, fractured, and came apart in stages. No one watched 3 miles of rock drop suddenly. If you encountered a headline suggesting the seafloor dropped 3 miles in a sudden event, that headline misrepresented what the study actually found. But the detail that is genuinely unsettling is quieter than that number and harder to sensationalize. Along the 75-kilometer fault structure, some sections remain seismically active while others have gone completely silent. In conventional seismology, a silent fault segment is typically the alarming one. Silence usually means stress is accumulating with nothing releasing it. Here, the researchers read the silence differently. The quiet zones most likely mark places where the slab has already fully detached. They are not accumulating stress because they are no longer mechanically connected to anything. Shuck described the process as watching a train derail one car at a time. Progressive, episodic, irreversible. The process has a formal name in the literature, episodic termination. Northern Cascadia's subduction is not heading toward a single catastrophic collapse. It is winding down one fragment at a time, and has been doing so for approximately 4 million years. The mechanism that drives this is the Nootka fault zone, the structure separating the Explorer plate from the Juan de Fuca plate. Transform faults act like geological scissors. Over millions of years, motion along this boundary has been cutting the oceanic crust into progressively smaller and more independent fragments. Each time a fragment detaches, it reduces what geologists call slab pull, the downward gravitational tug of the plate's own weight that drags the rest of the sheet into the mantle. Less slab pull means slower subduction. Slower subduction means more strain is absorbed by internal deformation and tearing. More tearing produces more detached fragments. The process reinforces itself, which is why it has been progressing for 4 million years and is projected to continue for roughly 1 million more. The Explorer plate is expected to fully detach within approximately that time frame, shortening the active Cascadia subduction zone by about 75 kilometers, roughly 1/12 of its total length. Geologists had long suspected that subduction zones terminated this way. They had seen the fossil evidence in ancient plate fragments preserved off Baja, California, remnants of the Farallon plate that subducted beneath North America tens of millions of years ago. Those fragments were the archaeological record of a subduction zone that had already finished dying. Cascadia is the living version. The first modern subduction zone caught actively disintegrating in high enough resolution to observe individual tiers as they form, and it comes with a specific caution the study authors made explicit. These findings do not change the current earthquake hazard for the Pacific Northwest on any human timescale. The tearing proceeds at millimeters per year, slower than your fingernails grow. Cascadia remains fully capable of producing magnitude 8.5 to 9.0 earthquakes, and the tsunamis that accompany them. The fault that everyone in the Pacific Northwest actually worries about is not the one that ruptured Sunday night. It is the megathrust interface itself, the locked contact zone where the Juan de Fuca plate is being forced beneath North America along a boundary stretching approximately 100 kilometers from Northern California to Vancouver Island. Along most of that length, the two have been accumulating there continuously since the last time it fully released. That release happened on January 26, 1700. 326 years of accumulated strain. The USGS has assessed the probability of an approximately magnitude 9 earthquake on the Cascadia subduction zone at 10 to 15% over the next 50 years. Oregon Emergency Management figures place the probability of a magnitude 7.1 or greater megathrust event at roughly 37% over the same window. When that interface finally ruptures, coastal communities on the outer Pacific coast could see tsunami run-up, reaching as high as 100 feet in the most vulnerable locations. Now, the question that Sunday's earthquake forces into focus is not whether Cascadia will rupture. The geological case for that is settled and has been for decades. The question the earthquake raises is more specific and considerably harder to answer. Does change how a future megathrust rupture would behave? And there are two competing possibilities, both consistent with the published mechanism, and researchers are working to distinguish between them right now. The first possibility is that the detached and fragmented sections of the Explorer slab could act as partial barriers to rupture propagation. If a megathrust rupture initiated somewhere in the central or southern Cascadia margin and propagated northward, it might encounter the structurally disrupted northern segment and slow down, deflect, or stop, rather than running cleanly through it. That would make a full 100-kilometer rupture less likely in the northern segment, and a shorter segmented rupture more probable there, which carries its own implications for shaking. Intensity and tsunami generation in specific locations. The second possibility cuts the other direction entirely. The additional internal faults, the independent blocks, the extra degrees of mechanical complexity at the northern margin could represent additional locations where stress concentrates and where rupture could initiate rather than terminate. More fractures means more ways for accumulated strain to find a release path. Scientists at the Cascadia Region Earthquake Science Center are incorporating these newly imaged structures into updated hazard models at this moment. The answer to which scenario is correct, barrier, or living in Vancouver, Victoria, Seattle, and the surrounding region. That answer is not yet in hand, which means the intellectually honest position is to hold both possibilities simultaneously and watch what the data produces. And the data from Sunday night's earthquake is still coming in. Here is the specific thing worth tracking over the next several days, because it is checkable by anyone with access to a seismicity map, and it is the most diagnostic signal the event will produce: the aftershock pattern. If aftershocks from the magnitude 5.6 remained clustered near the main rupture point out in the oceanic plate, that is the signature of an ordinary intraplate event, internal deformation of a fragmenting slab releasing accumulated stress, and it is essentially over. The energy dissipated locally, the way it is supposed to. But if aftershock activity begins migrating eastward toward the subduction front and the locked interface beneath Vancouver Island and the Washington coast, that warrants a different level of attention. Eastward migration would suggest the stress released by Sunday's rupture is being redistributed into the locked zone, that the perturbation reached the interface, and that changes the monitoring posture. There is direct precedent for this kind of scrutiny, and it is actually encouraging. On April 24, 2014, a magnitude 6.4 earthquake struck this same region, followed by an extensive aftershock sequence that became known in the literature as the Nootka sequence. A 2020 study in Earth and Planetary Science Letters analyzed that sequence and uncovered something that had not been previously mapped: an approximately 40-kilometer-long subducted fault inside the Explorer plate running north of the Nootka fault zone. The largest aftershock, a magnitude 5.3, arrived roughly 13 minutes after the main event and approximately 20 kilometers to the southeast. Hypocenter. Analysis showed the subducting plate bending nearly perpendicular to its expected subduction direction, deforming parallel to the margin rather than sliding cleanly beneath it. The plate was not behaving as the simple two-plate model predicted, and that 2014 sequence, at magnitude 6.4, released approximately 16 times more energy than Sunday night's 5.6. It did not trigger a Cascadia megathrust earthquake in this area, but it is the most directly relevant comparison available, and it points in a stable direction. The physics of stress transfer deserves an honest hearing here because it is frequently misrepresented in both directions. Every earthquake does change the stress field around it. Near a rupture zone, some neighboring fault sections are pushed slightly closer to failure, while others fall into what seismologists call a stress shadow, a zone of temporarily reduced stress where failure becomes momentarily less probable. These effects are real, documented, and well understood. Dynamic triggering, in which passing seismic waves briefly perturb distant faults, is also a documented phenomenon. None of that is in dispute. What is in dispute, or rather what is simply a matter of scale, is whether a magnitude 5.6 can meaningfully load a system accumulating strain at the rate Cascadia does. A magnitude 9 earthquake releases approximately 126,000 times more energy than a magnitude 5.6. The permanent stress change from Sunday's rupture is concentrated around a fault measured in kilometers. The Cascadia locked zone runs for hundreds of kilometers and has been accumulating strain continuously for 326 years at 40 millimeters per year. A small perturbation at one end of that system does not load it. If the megathrust is approaching failure, it is approaching failure because of 3 centuries of tectonic forcing, not because of one moderate sideways slip out on the explorer plate. Strip away the alarm and the reassurance both, and here is what remains. The explorer plate is being dragged downward beneath North America, while simultaneously being compressed and sheared by everything surrounding it. Because its sections move at different speeds in different directions, it cannot hold together as a solid block. It deforms internally. On Sunday night, one of its steep internal fractures accumulated more stress than the rock could contain, and it failed. That is what a magnitude 5.6 in this location, with this mechanism, most probably represents. Not a countdown, not a warning shot. The normal ongoing signature of a plate coming apart in slow motion, doing exactly what the geological record and the Shuck team's imaging predicted it would do. But the genuinely unsettling implication is not that the big one has begun. It is narrower and stranger than that. We can now image the northern end of Cascadia in enough resolution to watch it disintegrate in real time. We can project that process forward 1,000,000 years with reasonable confidence. What we cannot yet say is whether the most structurally broken section of this fault system is the part most likely to stop a future megathrust rupture, or the part most likely to start one. That question is open. Researchers are working on it. The answer matters enormously for several million people living within the rupture zone. 3 things will move that answer forward in the near term. The direction. Sunday's aftershocks migrate over the coming days is the first and most immediate signal. Clustered near the main shock means routine intraplate deformation. Eastward migration toward the locked interface means elevated monitoring attention. Second, whether refined hypocenter solutions eventually tie Sunday's rupture to a specific mapped structure, as the 2014 Nootka sequence took years to fully resolve. Third, whether updated Cascadia region Earthquake Science Center hazard models treat the newly imaged tiers as rupture barriers or as rupture initiation boundaries, because that distinction has direct consequences for how northern Cascadia's hazard is communicated to the public. In the meantime, the practical lesson was not delivered by the seismology. It was delivered 48 hours earlier by Peru, where a magnitude 5.5 at the same approximate depth killed at least 6 people, injured more than 30, and collapsed a church that had stood since 1565. Same magnitude, same depth. 6 dead in one case, 0 in the other. The variable was not the earthquake. It was building stock, construction quality, and geography. Sunday's 5.6 caused no harm because it happened in open ocean 200 kilometers from the nearest town. Place that same rupture beneath a populated valley, and the story is entirely different. That is the real takeaway from this event, and it is the one that applies whether or not you live anywhere near Cascadia. If you found this breakdown useful, share it with someone in the Pacific Northwest who deserves to understand what is actually happening beneath that coastline. Subscribe if you want coverage that goes past the headline and into the mechanism. The next update on Cascadia's aftershock pattern will matter. This channel will be watching it.